Hello and good day. So we're now approaching almost the end of General Physics 1. And yeah, I know we only have discussed linear motion as of far. But what can we do, right? All I can hope is at least we have learned something on this course. And hopefully you will be able to remember all of this once you take your college courses, whether it will be under engineering and physics or something related to biology or computer science. I'm 100% sure that physics will always be present one way or another. So for our module 9, so this will be like the second to the last module, we're going to discuss momentum and impulse. So I think it will be further discussed, the concepts, to you by your subject teachers. But for now, I'm going to stick with very approachable definition of momentum and impulse. Then at the same time, show it to you how it is mathematically processed. No? So first, let's define momentum as the measurement of how difficult it would be to stop an object from moving. Okay? Or how difficult it is an object at the same time to cause it to move. Something like that. Okay? So it is a vector quantity which is a product of mass and velocity. Okay? Then it can also be defined as mass in motion. But it can also be defined as mass, inertial mass, which is at rest, and how difficult it is to move. That's momentum as well. So that can be mathematically defined as rho. Some of your teachers might use P instead to designate the variable for momentum. Then we have mass times velocity. Okay? So fundamental SI unit for momentum is kilogram meter per second. So there's no, like, for example, like energy or work, we have joules. For force, we have newtons. No. For momentum, it's purely in fundamental SI. So that's in kilogram meter per second. Then we have impulse. Okay, so impulse is the measurement of change in momentum, which can be obtained through the product of force and time. Okay, so that could be shown using this formula. So that's impulse, which is J, is equal to force times time. Okay, and then of course our SI unit would be newtons seconds. Okay, so that's multiply, alright, not divide. Okay, so I'm going to show you something. So knowing that this is mass times velocity, and then J is force times time, right? Since we're going to derive this one, so I'm going to show you that you can rewrite J as force is what? Mass times acceleration, right? Multiplied by time. And then acceleration can be written as mass times velocity over time, right? Multiplied by time, correct? So as you can see, you can cancel out time because that's divide, right? So you'll end up with J equal to mass times velocity. And then since this is momentum, you can see, you can now describe momentum as impulse. This is what we call as the impulse momentum theorem, or momentum impulse theorem, however you want to call it. So basically they're the same thing. If you want to show it in units, so in this case you want to show this in units, so this is what? Newton seconds, right? Then you can expand Newton to what? Mass times acceleration, so that's kilogram multiplied by meter per second squared times seconds. So you can cancel this, so you're left with kgm, which is the same unit as this one, which is mass times velocity. Kgm over s, sorry, over s. Here. Got that? Okay, so mathematically it's really easy. So let's try to jump into guided practice problems and solve some. Okay, so for our first problem, we have a truck which has a mass of 10,000 kilograms and a speed of 12 meters per second. Okay, so let's try to solve for its momentum. So very easy, just a really easy first example. So you can like illustrate it. So let's have an SUV there. So let's just assume this is your SUV. So this is the mass moving at a certain velocity, right? So let's write our given. So we have mass which is equal to 10,000 kilograms, right? So upon arriving on this stage, you can actually rewrite it as what do you call this? Scientific notation. Okay, then for speed, we have 12 meters per second. Okay, for our first required, we are asked to look for the momentum. Correct? So for our equation, so that's rho is equal to mv. Okay, this is rho, Greek letter rho. I think I've shown it on the PowerPoint earlier, so you can just return to that particular time and pause it. Alright? For our solution, so this is like really easy, right? So for our solution, you can just write 10,000 kilograms multiplied by 12 meters per second. So that's it. Then your answer, let's just rewrite it in SI, right? Okay, so we're going to have 1.2 times 10 raised to, so this is 120,000, right? So how many decimal places would that be? That would be 5, right? So our unit is in kilogram meter per second. There. That's our momentum. Just box it and that's it. Okay, as for our second problem, so we're asked the velocity of a 2,000 kilogram SUV if we want to attain the same momentum. Okay, so for our second problem, so we have a given of momentum, right? So that would be 1.2 times 10 raised to 5, so that's kgm over s. Okay, and then we have a mass which is 2,000. For our required, we are looking for velocity, right? Then for our equation, we can show the derivation, but it's really easy, so you can just go straight at it. Doesn't matter. As long as it's just a one-step process, it's fine. So you have velocity is equal to, so I'm going to expand this one, so we'll be able to show the cancellation. kgm over s. Okay, so divided by, what's this? 2,000. Okay, so we're going to cancel, of course, kilogram first. Then we can cancel the zeros, so that would effectively be division. So that's 1,000 divided by 1,000. So it will become 120 divided by 2. Is that right? Okay, of course that's right. So what's our answer? Our velocity will be 60. Correct? Then of course our unit would be meter per second. There. So I think you got that one, no? So that's a bit easy, right? So let's proceed on guided practice problem number 2. So let's move this one to the next page instead. There you go. Okay, so we're asked to, in a certain track and field event, the shot put has a mass of 7.30 kilogram and is released with a 15 meter per second at 40 degrees above the horizontal over the competitor's straight left leg. What are the initial horizontal and vertical components of the momentum of the shot put? So this is incorporating one of the topics that we had before. So it's of course projectile motion. No? So first let's write what do you call this? The diagram for this one. So we have a shot put going at a certain velocity. Is V. Let's name this V sub 0. Okay. Then of course we're going to break it down to its vertical and horizontal components, right? So I'm going to use this for our vertical, then this one for our horizontal. Okay, so our vertical would be what? V sub y sub 0, right? Then for this one, this will be V sub x sub 0. That's it. Then we have an angle, which is of course 40 degrees. You got the idea. Okay, so let's proceed. We have given, which is, first we have a mass. So let's place a mass here. Okay, so that's what? 7.30 kilograms. Oh wait, variable, so 7.30 kilograms. We have initial velocity of 15 meters per second. Okay, then we have an angle of 40 degrees, right? Then we're asked for momentum, so that would, I would write it in this way instead. So mx sub o and then mv y sub o. So that's basically still momentum naman, right? So for our equation, of course, generally we have rho is equal to mv. So for mv sub x sub o, we have, oh yeah, that's basically that, no? So let's rename this what? Rho x sub 0. So that would be mv sub 0, and then rho y sub 0 would mv sub y 0. Okay, so for the solution, you can just write it independently, no? So you can have, so let's have rho x sub 0 would be what's this? What's our mass? Oh, forgot the unit here, so don't forget your units. All right, so that would be 7.30 kilograms. So our velocity is 15 meter per second cosine 40, right? Then that's it. For our y, I'm just going to write it first now for proceeding. So we have 7.30 kilograms, and we have 15 meters per second sine 40. I think you got that, what do you call this, definition as of this point. So I'm going to solve it first. So that's 7.3 times 15 cosine 40. So what's that? 83.88. Okay. So unit, of course, kilogram meter per second. And then for our sine, so that would be what? 70.13. Correct? 70.13 kilogram meter per second. Then you can proceed now on the answers. So for rho sub x sub 0, so that would be 83.88 kilogram meter per second. Then for rho sub something like this, so this is 70.39, okay, kilogram meter per second. Then you can just box it there. So did we miss anything? So that's it. Okay, So yeah, if you have more questions, you can just ask your subject teachers about it. All right, so let's proceed on our next problem now. So for our guided practice problem 3, we are provided, oh, this is just straight impulse, right? So this is easy. Actually, the topic is really easy. So you have a ball which is being pitched, right? So it has a certain velocity, then this ball has a certain mass. Then basically that's it. Huh? So let's proceed on writing our given. So we have, so I hope you're finding this topic easier compared to the ones that we have before. But of course, you can explore other aspect na, of the topic. I'm going to show you later some derivation no, on the what do you call this, equations that you might arrive with regarding this topic. So for our equation we have, so you can just write mv, or you can, if you want, you can use j is equal to mv as well. They're basically the same. So for our solution, so that's just rho is equal to, so we're already on an SI unit, so you don't have to convert anything else. Kilograms multiplied by 45 per second. There. So are we missing anything else? Oh, no such thing. So you can just proceed on finding the final answer. So that's 0.145 multiplied by 45. So that would be 6.525 or 6.53. Our unit is of course kilogram meter per second. There. So that's easy, no? Okay, let's try to answer the last one. I think this will give you a bit of a challenge. Okay, so to warm up for a match, a tennis player hits the 57-gram ball vertically with her racket. If the ball is stationary just before it hits and goes 5.50 meters high, what impulse should it impart to it? Okay, so we can approach it in few ways. So I'm going to do one. So I'm going to draw the ball first. Okay, so this is what our delta y, right? Then we have what, mass. So we don't have velocity for that matter, but we can obtain that. So first let's have our height, which is 5.50. So that's it. Then we have mass, which is, what's our mass? 57 grams. So let's convert this to SI, no? So this is what, 1000 grams, 1 kg. Cancel. So that's 57 divided by 1000. What's that? 0.057, correct? Let's check. But of course that's correct. So that's a unit. For our required, we're looking for, in this case we have impulse, so let's follow the convention. For equation, you can have, I don't know, let's try to stick on MV because I really prefer this approach. Okay, so let's derive, no? So for us to obtain velocity, we can first look at our scenario. So we have displacement, then of course we have this magical number, which is of course the acceleration due to gravity. So we can obtain that. So our velocity in this case, so that would be, what equation can we use? 2g delta y, right? Square root. Correct? Coming from the fourth kinematic equation. Diba? This is derived from the fourth kinematic equation. V squared equal to V sub 0 squared plus 2g delta y. Okay? You can approach it by utilizing the initial velocity. So how about we try to do that? But you're going to have a negative answer. But you can cancel that one out, so it will still be the same. So what would happen is you can cancel this one out, then this will be something like this, equal to 2 times negative g delta y. Correct? You can cancel this one out, but will still be the same. Right? After canceling, you can look for the square root. Okay? So in this case, it will be initial velocity, the velocity that we're going to utilize. Because of course, reaching the maximum height, our v here is what? 0. Correct? So we have velocity on this side. That's the case. So we have a certain value, which is of course what we're going to obtain. So since this is equal to that, so we can now rewrite j is equal to m times square root of 2g delta y. Okay, and then since we canceled the negative sign already, you don't have to worry about it. So for the solution, you can now rewrite it as j is equal to her mass 0.57 kilograms, okay, multiplied by, so this is 2 times 9.8 meter per second squared multiplied by 5.5 meters. Okay, you can double check. So meter times meter is meter squared. Then you're going to, of course, cancel those using, because you have square root, right? So you're left with the unit meter per second multiplied to kilograms. So you're basically obtaining the unit for momentum, or in this case, impulse. So yeah, of course, you're still going to operate on the square root on the number, so don't forget that. We're just canceling it on the side of the units. Okay, I hope you still, wait, I wrote this wrong. So that's 0.057. Okay, so there. So 0.057 multiplied by square root of 2 times 9.8 times 5.5. There, so what's our answer? There you go. So our momentum, or impulse in this case, is 0.59, right? So it's 0.59. Okay, that's it. Our unit is of course kilogram meter per second. There. So I hope you got that. If you have questions, then ask me, of course, or your subject teachers for that matter. Okay, so I'm still going to post this, but if you want to go straight into the self-paced practice problem, you can just check it here. So here's the problem for self-paced 1, so you can just pause it and take a look. SP2, here it is. Okay, for SP3 we have this one. Okay, and then lastly for SP4, there you go. So that concludes our discussion basically. No, it's a bit easier. All right, then for our next meeting, we're going to tackle about the conservation law, actually focusing on momentum. No, we already had conservation laws on the previous topic. That's law of conservation of energy in a sense, the work energy theorem. In this case, we're going to have conservation law on momentum. Okay, so yeah, that's it. Thank you so much, guys, and of course, you have a good day.